Assalamu alaikum everyone. This is our course EEE 4403. EEE 4403 Communication Engineering 1. So today's our topics is amplitude modulation. Or AM. So amplitude modulation is an analog communication scheme that one of the earliest actually communication scheme developed and widely used and often abbreviated as AM. Now for any communication scheme there involves a carrier signal, right? So there involves a carrier signal. So let us mention that for our case carrier signal is CT, which can be mentioned as AC, amplitude of the carrier, cos 2 pi FC T. Here this FC is the carrier frequency. So this is the carrier frequency. So this is the amplitude or carrier amplitude of the carrier and this is the carrier signal. So what happened in amplitude modulation, the carrier will be modulated by the message signal. That's the fundamental concept. Okay. Now, what is this AM then? So, AM is the message modulates amplitude of carrier. So, in AM, message modulates amplitude of carrier. Okay. So, what is the message then? The message signal is, so we can hear AC cos 2 pi FC T. This is actually our carrier signal. And what is the message signal? 1 plus K MT. This is actually our message signal. Here is the message. And this is the carrier. Okay. So, what is the amplitude modulated signal then? So, the final signal came, or amplitude modulated signal came as 1 plus K MT multiplied by the carrier AC cos 2 pi FCT. Or we can write it other way, that AC 1 plus K MT cos 2 pi FCT. So here, this is the amplitude modulated signal. This is actually the amplitude modulated signal, where this K, this K, A, we can write it A, amplitude K, A, K, A, where K, A is the sensitivity. A, sensitivity, and MT is the message signal. Message signal. Right? Okay. If this is the case, then amplitude of the carrier is varied or modulated according to the message signal MT. So we can see if this is a time dependent message signal which will actually ultimately change the total amplitude, this portion of the carrier. So this is the carrier signal and this is the amplitude of the total amplitude of this carrier. This whole portion is the total amplitude of this carrier. So the amplitude of the total amplitude of this carrier will be varied by this message signal MT, which is a time dependent. So we can write amplitude of carrier which is actually this one. Amplitude of the carrier is varied or we can say modulated according to or by the message signal or by the varying of the message signal according to message signal MT, where MT is the time varying message signal, right? Okay, so we can give you an example. So we can take some example. So we can say here 1 plus this one, total. You see here what we just see, this amount will influence the amplitude of the carrier, which was the fundamental amplitude or the basic amplitude before. So now this amplitude is varying according to this amount, right? So according to the message signal. So when we multiply the message by the carrier signal, the amplitude of the carrier, which is previously a constant, is now time varying in nature, and it varies as per the message MT. That's actually this portion mean. Our previously amplitude was a constant value, this one. Now we multiply with the message signal, where our ultimate modulated signal, the amplitude of the modulated signal AC is no more a fixed quantity. It varies according to the time varying quantity MT, which is a message signal. Okay, let's take an example. Where in our example, in this our example, we say AC equal to 1, Ka equal to half, and FM, the message frequency, is half. If this is the case, then what is MT then? If this is the case, what is MT? So MT So MT is nothing but what? Message signal. Here we just wrote here MT, which is a message signal. Okay, so we can write message signal. Message signal is cos 2 pi fmt. We didn't define it earlier, so let's define it now. So for this case, because fm is half, which is actually this one, half, so it becomes cos, so 2.5 cross, so pi t. This is our message signal. If this is the case, what is the amplitude modulus signal came? Okay, so amplitude modulus signal came as what is AM signal? So amplitude modulated signal or amplitude modulated signal. What is that? AM xt. We are looking for xt. This is the case. Then what is xt? What is this xt? So xt is AC is 1 now. AC is 1. Here AC is 1. So 1 plus K is half here. K is half. What is MT? MT is cos pi t. Half cos pi t. And cos. Okay, this is our message comes. Okay. Okay, and this portion remains. So cos 2 pi fct. Our carrier is multiplied. Okay, so if this is the case, then we can rewrite the xt here, right? Okay, this is actually our modulated signal. So we choose the sensitivity Ka is half, and message is a we choose the message is a pure sinusoidal signal, which is this one. Message is a pure sinusoidal signal. Now let's draw it. Just draw this signal here. Let's draw this signal. Okay. So modulating signal. So here, what is the maximum and minimum value here? We can see here if cos this pi becomes 0, cos 0 degree is 1. So 1 plus half, so 3 by 2. So this becomes the maximum value becomes 3 by 2. So if this is, so this is a time varying t. So this is, for example, 1. This is 2. So maximum value is 3 by 2, right? At 0, cos 0 degree. At 0. Okay. Cos 0 degree. So 0. Say this is 1. This is 1. Say this is 2. Say this is 3. Okay. So here is the like half. This is 1. This is 2. Amplitude 2. Here 3 by 2 is actually half. So I want to make it little bit bigger, okay, to make a better understanding. So let's give this notation little bit bigger notation. It will be easy for me to draw it if it's bigger. say this is 1, say this is 2. In that case, this is half, this is half. This is 1 and this is 2. So 3 by 2 is half. Actually, half is here. So 3 by 2 is here. Okay. Now, if this is the case, then what is the minimum value? Minimum value is cos pi. Okay, so t equal to 0 makes cos 0. This is t. So imagine this is 0. So t equal to 1, this become cos pi. Okay, cos pi is minus half. So it will be minus 1. So 1 minus half will be minus half. So this is actually our minimum value. Minimum value. So this is our maximum value. This is minimum value. So accordingly, this is will be minus 1. This will be minus 2. And here somewhere this will be minus half. This is minus half. So at t equal to 0, 0, what is the value? Maximum value 3 by 2. So t equal to 0, this is the maximum value. Here is the maximum value. Okay, so let us point it. So this is the maximum value. At t equal to 1, this becomes minus half. At t equal to 1, it becomes minus half. So this will be the point. I beg your pardon. At t equal to 1, cos pi is 1. So minus 1. So 1 minus half will be half, actually, not minus half. It's positive half. So this will be the value. I beg your pardon. So not this one. So this is the value where at t equal to 2, again, this will be the value. At t equal to 3, approximately here will be the value. So if I draw it, if I connect this dot, then it will look like this. Please bear with me. So here, okay. This point should be a little bit here. Yeah. Okay, so it will be like this. Like this. Okay. So if this is not a smooth one, if I make it a smooth one, it will look like this. Let us draw it smoothly. Kind of like this. Okay. So this will be the my this will be my positive side. So in the other side, it will be actually the shadow or the reflected version. So if I complete, so if I complete 3 by 2, it will be somewhere here, right? Yeah. Something like that. Something like that. So the carrier will be inside. So the carrier will be inside. If I draw the carrier, sorry, it's not only nice. Again, it's not looking nice. Something like that. So this is actually our carrier. Anyway, you got the idea. So this is our carrier signal. So if I denote here, if I denote here, so this is actually, this signal is actually our carrier, this one. This is the one where its amplitude actually varying according to the message signal. Now, this portion is called the envelope of the carrier. Envelope of the carrier. So we can see in this picture that amplitude of the carrier is modulated by the message. Therefore, the envelope of the carrier contains the information about the message signal. So here we can say the amplitude of carrier, which is actually this one for our case, this one, amplitude of the carrier, because you see here this portion, here the amplitude is changing, amplitudes keep changing of this carrier. So amplitude of the carrier is modulated by message. Means the envelope of the carrier contains the information. So envelope of carrier contains the message. So envelope of the carrier contains the message. Okay. Now the perfection of this idea, where the envelope of the message of the carrier is actually containing the message, the condition is Fc, the carrier frequency should be much higher than the Fm. So this is a condition. If we want to impose the message on the carrier, this should be the condition. The Fc, the carrier frequency, should be much higher than the Fm. It's obvious, right? You see how we have this envelope at the first place, because this is actually the tip. If you connect all the tips of the or trace of the amplitude of this carrier, trace of the amplitude of the carrier, then actually you reconstruct. Means higher the frequency, this will be precise. For example, if I give you an example here, for example, this is, if I draw a simple version of this one. For example, this is the, so if for example, if I draw the carrier like very high frequency, very high frequency. See, I'm increasing compared to the previous picture. Here the frequency is very high compared to this picture. Here you can see the tip is very close, very close. So the information is more reliably constructed here, because for the sake of simplicity, our carrier is actually it's little bit low frequency, right? You see the difference between this tip and this tip is quite far, but here it's actually quite close. Means actually the more higher the frequency of the carrier, the message will be more inbuilt here. Okay, so this is our this is the carrier frequency, and that is the message frequency. So carrier frequency, and this is the message frequency. Message frequency. Okay, so we will change our parameters now again. So previously we draw this picture for this assumption. What are the assumption? These are the assumption. S equal to 1, K equal to half, M equal, Fm equal to half. Now let's change it. See, by changing parameter, how it affects our total assumption. Now, here we actually assume K equal to 3/2. We are increasing the sensitivity actually. So what remains same? AC was 1 and FM was half. Here only the sensitivity, we are changing the sensitivity. Previously it was 1, now we increase it. 3/2 actually half, 1.5. So we are increasing the sensitivity. Let's see if this is the case. Then again we need to find what is the maximum value, what is the minimum value. If this is the case for this xt from this portion, this portion, how much we get. So if k equal to 3/2, right? K equal to, let's say k equal to 3/2. What we write from here? Sorry, this one. So S equal to 1, Ka equal to now 3/2. Okay, let's draw write this message signal. Let's write this xt signal. So xt, assuming k equal to half, what is xt? Xt becomes AC was 1. AC was 1. What is the equation? AC 1 plus kmt. So 1 plus k. K is 3/2. Mt. What is mt? Mt is a message signal, which is actually this signal. This signal cos pi t. Cos pi t multiplied by the cos 2 pi fc t, this one. Okay, so here what is the maximum value and what is the minimum value? So here the maximum value will be what? So we are finding the maximum value of this portion, and the minimum also, What is the maximum value? So maximum value is at t equal to 0. Okay, let's again draw it. Let's again draw it. We actually drawing it in time domain, right? So maximum value t equal to 0. So here t equal to 0, say t equal to 1, say t equal to 2, say t equal to 3 here. Okay, so if t equal to 0, cos 0 degree is 1. So this portion becomes 5/2, which is actually 2.5. And the minimum value will be minus. So 1 minus 3/2. Okay. So which is actually half, minus half. Okay. So at t equal to 1, cos pi equal to minus 1, which makes 3/2 minus 3/2. So 1 minus 3/2 becomes half, minus half, sorry. So for 0 t equal to 0, the maximum value is 5/2, which is actually, so for our case, say this is 1, this is 2. Okay. So this is 1, sorry, and this is minus 1, this is 2, minus 2. So this will be minus half. This is actually plus half. Okay. So for maximum value 5/2, which is actually 5/2 is 2.5, right? We made some mistake on the, okay. So it should be somewhere here, 2.5, which is actually 5/2, which is actually also 2.5 will be somewhere here, minus 5/2. Okay. So 1 point will be here for maximum t equal to, when t equal to 0 is the maximum value. When t equal to 1, t equal to 1 is minus half, t equal to 1, which is actually minus half. And again, for t equal to 2, it will be 5/2, and t equal to 3, it will be minus half, like this. So if this is the case, then if this is the case, then let us add those dots. Uh, I'm trying to draw it as smooth as possible. Okay, something like that. And the mirror version will be, so this will be the opposite one, this one, like this one, and kind of this one, right? Okay, so it will be like this. Trying to draw it as smooth as possible, kind of like this. Okay, so if I draw the carrier inside here as smooth as possible, be like this. Sorry, it's not straight, it should be a straight line. Mm, okay. trying to draw it as smooth as possible, or you get the idea actually how it works, something like that. Actually, I'm drawing the carrier here. Something like that. Okay, you got the idea. Okay, so here, what are those values? Okay, so we can see who is this. This is actually, or who is this? This is actually our carrier, right? What is our carrier? Whatever it is a carrier. It is our carrier. What is this one? This one is 1 plus Ka empty, the message signal, right? This portion. This portion. This portion. Okay, so for our cases, 1 plus K empty, that part is the message one. Okay, what else is here? If this is 1 plus KMT, then what happened here? What happened here? This is very noticeable point. This point. This point is very noticeable point. We can draw it here. That at 1 plus KAMT, one, this becomes by providing our these values, Ka equal to 3/2, S equal to 1, and Fm equal to half, then this becomes 1 plus 3/2 cos pi t, cos pi t. At this point, it's 0, means at this point 1 plus kmt starts becoming negative. So 1 plus KAMT starts becoming negative. See here, you can see the phase here. This one goes, and here the phase changes. It becomes the negative one. This is called the phase reversal in modulating signal. This is actually phase reversal. So this point also here is the phase reversal. Phase reversal in modulating signal. In modulating signal. Why this happens? Because of this. We change the value excessively, and because of this, now for example, this signal will be detected at the output. So the detector will, instead of this red red envelope, the detector will detect it like this. Understand? So he actually missed this portion in detection, because at the beginning, what was our signal envelope should be at ideal cases. So this is the one, this is the one, this should be the ideal one, this should be the ideal one. But because of this phase reversal, these will be detected only. This portion will be detected. These will be detected as, right? Like this. then these will be detected, then this. So this is called envelope distortion. So these, so this phenomena where this happens, so this is called envelope distortion. So we can find from here why the envelope distortion happens. It happens because of this value, because of this this parameter. Now to avoid this distortion, so we can write, so to avoid envelope distortion, choose Ka properly or properly. This should be Ka, the sensitivity should be detected properly. Means this value 1 plus Ka mt should be greater than 0. For no distortion. This is for no distortion. Means Ka, the amplitude of this minimum mt message signal should be less than or equal to 1. Okay? If I take this one other side, so it becomes less than 1. So this is the condition. This is actually the condition for no distortion or distortion less envelope distortion, for no envelope distortion. So we can write this is the condition for no envelope distortion. So by 2 example, we find that there is a condition which must be satisfied. To this amount is called the mu or modulation index or modulation index. So mu should be less than 1. So this should be the value. So mu should be the less than or equal to 1. If otherwise happens, means if mu is greater than 1, then that condition is called over modulation. Over modulation, which happens in this case. In our case, previous case, over modulation happens because of that the distortion happens. Okay. Now for this case where we have the normal case, for this case mt, the message signal is, we already wrote it, cos pi t, right? Pi t. What is the minimum of this message? What is the minimum value of cos pi t here? Let me check if the recording is on. Yeah, the recording is on. So for but two of the example, our mt is equal to cos 2 pi t. So therefore, the minimum of mt is basically the minimum of cos pi t, right? Which is actually basically the minimum of, because mt is equal to cos pi t, which is replacing cos pi t, which is actually what? Which is actually nothing but what is the minimum value of cos pi t is -1. When cos pi value is -1, so minimum, and this amplitude is 1. Okay. So if this is the case, what happened? If this is the case, then what is the mu value? Mu value is, you see, we find the value of mu here. The mu value is Ka minimum of mt. So what is the Ka minimum of mt? So Ka into minimum of mt, which is actually 1, where Ka is also value of half. We actually took this value earlier, right? K is half. K is half. K is half. So we put half into 1, which is actually half. Is this value greater or less than 1? Yes, this is less than 1. So if this is less than 1, then this condition satisfy. This condition satisfy for no envelope distortion, which is actually less than 1. Means no distortion condition happens. Distortion. So no distortion, and we can see in this example, no distortion happens. But for the other condition where Ka was 3/2, right? So K equal to, where it was 3/2. Yeah, so here it was 3/2. But Ka equal to 3/2, what happens to this value? So Ka equal to 3/2, this condition, what is the mu value comes? Mu equal to, we can write that Ka is the minimum of like mt is value comes as, what is the minimum value of mt or cos Ka equal to 3/2, 3/2. What is the minimum of mt for this case? We see here the minimum value cos 5 minus half. Which is actually half, because is only amplitude is considering, right? This is, though this is minus half, but the amplitude, which is actually let's see how it comes. Okay, so I beg your pardon, I made a mistake here. So this should be rewritten here. Okay, so k is k equal to 3 by 2. 3 by 2 into, so cos empty, what was the message? Our message was empty was cos pi. What is the minimum value of pi? Which is actually the 1 here, what we actually wrote here, -1, which actually ultimately becomes 1. So this one, cos pi t, right? So minimum value of cos pi t is equal to -1, which becomes amplitude 1, which is actually, for our case also, which is actually 3 by 2. This value 3 by 2 is greater than mu, right? Is greater than mu value. Means this is called overmodulation. Overmodulation. And we can see that overmodulation actually is happening here in this mechanism where the envelope distortion happens, right? So because of this portion, right, when the amplitude was crossing this value, is actually taking that value, that this was the value, instead of taking this is the value. So to avoid envelope distortion, choose Ka properly. That's the condition. That should be the uh, mechanism to avoid the overmodulation. So if overmodulation happens, the wrong envelope is detected. So the modulation scheme will not give you the proper message in the receiver side. So that's will end our today's lecture. Thank you.